Yeah, hello guys. I think so for I'll continue with this session. We will finish unit one. I think we are only left with examples for unit one. So I'll just record this video for the examples of unit one. We have done and everything. And I think we have covered all the distance between 2 points and everything. And yeah, let's start with our exercises. Now, for this unit, I think so I'll just inform you. Yeah, the following is most of the exercises. Yeah, very simple, and I think you will do. This is the easiest match you will do for this module. Then after that, we'll have more complex maths coming in. So I'll just go through these exercises and just explain few things. So we'll start here with what you call exercise zero, where they ask you to calculate the energy of a green light, which is given. So your green light has a wavelength of 500 nanometers. So that's your wavelength, or you can say your lambda. Then you have your orange light also, which has a wavelength of 600 nanometers. Yeah, well, this one is quite simple where they just ask you to get the frequency, which is what, and the formula is already given to. So you use this formula of frequency times lambda, then your lambda is given, and your speed of light is what? I think so it's uh, 3 times 10 to the power of 8. Let's just say, I think so it's 3 times 10 to the power of 8. That is your speed of light. Let's ionization. Yeah, it's 3. So that's your speed of light which is given to you. So yeah, you can go through that. So yeah, well, more or less that's what's going to show you. So use this formula to calculate your speed of or the frequency of the light, which is asked here. So it's quite simple enough. So I believe you do understand this part. Even exercise zero, where they ask you to calculate the energy of the system. So you use this formula of what this E equals f of h, and then I think so your h is given, which is times 10 to the power of it's given. Then even your frequency you calculated in the previous question or above. So that this one is also quite simple. So this is where you calculated your frequency. Then this will you use this formula to calculate the energy of your system. And then even exercise one is just matrix calculations. As you can see, you're given a matrix A and B, or a vector A and B. So to convert into matrix, it's quite simple. You can just say A equals your x component is 10, your y component is -4, and your z component is 6. Then for B, you will have your x component 2, y component is 1, and z component, there is no z component, which is 0. So that's 0. Then they ask the component of A along y. So they're just asking the coefficient of A and AY, this one. So that is what? -4. Then B, they ask you the magnitude, which is very simple. When this mean by the magnitude, so it just means they want the, I think so you do know from physics, they want the length of the system. Then unit vector, that's also quite simple enough. You have for this system, so you get the vector of this system, A plus B. If we go down, it's here, yeah. you get the vector, you add them together, you get your vector. Then unit vector is simple. You use this formula to calculate it, which is what you can say. They call it a over whatever you can say C to C. Um, so that's your gradient. I hope you understand this. This one is also quite simple, so I'm not going to go through it because it's just basic matrix or vector calculations you can go through. That's our one. Then exercise 2, maybe we can check this out. Let's try exercise 2. So on exercise 2, it's they say a river flows in southwest direction, so we can have something like this. Let's say this is our and then we have north, south, there. This is our east, and that is our west. Then they say a river is floating in this direction, southwest, right? At then the speed of the river flowing, or you can say, um, yeah, the velocity of the river, you can say it's 10 kilometers an hour. And then there's a boat floating on that river, which is also then it's following the same direction, right? The boat, so it will have the same direction. So we can say our boat is also floating in the same direction. Let's say this is our southeast, so it's going to be southeast exact 45 degrees. So that's our southeast. So this is where our boat is also floating. Just traveling. Then they ask a man is walking on the deck. So that's our boat. Then a man is walking exactly 90 degrees. So you can say exactly 90 degrees to the boat. So it's going to be more or less like this, somewhere here. So we have a 90-degree angle. So that's way of a man. And that could be our east line. You can say this will be 45. Yeah. Then they say find the velocity of the man respect to the earth. So finding the velocity, well, it's a mechanical question, but it's quite simple. So we want the velocity of the man with respect to the river, more or less. So respect to this angle of 45. But then you must also remember, well, the man is on the boat. So there's a law. It says the added velocity. So this is your boat, then that's more or less 90 degrees. That's your man here, and this is 45. So there's a effect of added velocity in the system. So for that, then we need to calculate the component of the vector in the same direction, the boat component, the same direction as the man. So this is where we first find what we call the component for the boat. So our UB is going to be, we call it the boat. Then the component of the boat, let's say the X and the Y direction, it's going to be 10. When the boat will be at so the same speed as the river because it's floating in the river, so it doesn't affect. Let's say it doesn't have a motor or something, so it's going to flow at the same speed as the motor. So the X and the Y component of the boat is going to be 45. Let's do this. Then let me close this. So our both the X and the Y components are going to be something like this. That's our 45 degrees. Then our X vector, or it's the direction. This shows the direction of the system, and then sine of 45. This will give us the y-axis of the system, which if you calculate, you can put in the calculator, but it gives you close to 0.071 ax, then minus the same 0.071 ay. So that's the direction of your boat. Then let's say, let me just change the orientation of the page. Might work better that way. Yeah. Then I'll just draw. So that's how the components for the boat, right? Then then for the component of the man is traveling at, so we take it, it's with respect to the boat. So we take the man's speed with respect to the boat. So his speed with respect to the boat is 2 meters cos, then it's still going to be what? And it's minus, so because it's traveling in the opposite direction of the boat. 45, the angle doesn't change, it's with respect to the boat. So the angle doesn't change. Then we have our a of x, our y direction is still the same. And then that's why then this will give us more or less minus 1.14 ax, and that is point minus 1.14 ay. So that's our, what do you call, the speed of the man with respect to the boat. So then what do we want is the speed of the man according with respect to the river, maybe. Yeah, I think so. They said, but I'll say river. It's much better to get that. No, we minus the speed of the man, or the boat, or it's mostly speed of the man minus the speed of the boat. So it's going to be v. Let's say it's going to be u. Then that's going to be your boat and the man, or you can say man and the boat. Your speed of the man minus speed of the boat. Then that should give you the direction, not minus plus, that should give you the direction in which the or the speed of the man on the boat with respect to the river. And if you add your those values, should get close to 5.57 ax, then it's going to be minus 8.485 ay. So that's our answer. No, it's simple. It's quite simple. Then you can also get the gradient of the system and the angle. That I'll leave it to you. Then we go to our next question. Yeah, our question 3 is the same thing. It's a simple vector multiplication, and in this case, they want the angle between the two variables, which is, I think so. It's quite simple. So to get the variables between the two components, you find the dot product and the cross product of the components. There are two methods. Either use the dot product or the cross product of the component to find here. I think so. It's cos theta AB. So you will find that angle, or for a cross component sine theta AB. Then here you will find your component. So that this one is quite simple enough. So I won't go through this. As you can see, they do use it. And even exercise 4 is simple vector multiplication, which I believe you should know. So you can do this for a practice or something, but it's very simple. So I won't even also go through this. I can just say you can convert those vector values like such as here you only have z, so you can also add 0 ay, so you have all the values here. So you can you only when you add these components you find the cross product, then first you get the cross product, then you get the dot product, because if you first try to get the dot product here it won't work. Right. So first what you do is mostly you get the cross product, then you get the dot product. So for this one I just want to give you a warning. First you get the cross product, then you will calculate your dot product. Yeah. So this is simple vector multiplication. You can go through this. Even here it's there. You can also check all these questions. Yeah, let's go to number 5. So number 5 is given here. So we have a point P and a vector A, which is in terms of y plus x and z. Then they said express P and A in cylindric and spherical coordinates. Then you evaluate A at point P in Cartesian, cylindric, and spherical. And I think if you can get one of them correct, let's say if you get the Cartesian or in this case the cylindric, the rest of them are quite simple enough. So I'll just show you how to get the, or what do you call it? Get a let's say in each case cylindric or spherical. Then from there it's quite simple. You can do it yourself, rest of them. So let's start. So let's start. So they say we have a point P, which is in the coordinates 2, 6, and 3. Then we have our A, which is on the coordinate of y of ax plus x plus z ay. So they say we must express what they call the first one is express P in terms of A, or express P and A. Yeah. So they want the cylindric coordinates of P, then they want the cylindric coordinates of A. So they say express P and A in cylindric and in spherical. So to express a P for in let's say in cylindric, if you can go back to the formulas, you remember we have our what do you call um we have our P component for not this P, it's this you, let me draw, yeah, for a cylindric component we have our this which is x squared plus y, right? So here you can will get our r. Here we'll get our r value, or you can say it's not the r value. Yeah, it's the phi value. I'm sorry. So you substitute the in the x and the y value for p. So which is minus 2 squared plus 6 squared, which will give you 40 square root, which is you can simplify yourself, then I think it gives you 3.62 and so on. And then to get the theta, because for cylindric we know our z value will be the same, it's y over x, so which is going to be Sorry. So it's going to be 10 minus 1 y over x, which equals, then if you put this into the calculator, 6 and minus 2, that gives you what, minus 3, which is, I think so, in degrees is 108 degrees. So so we are trying here to express our coordinates in cylindric. So our cylindrical coordinates will be how? Let's say p in terms of cylindric coordinates will be 3.62. Then this should be in radians. Just remember that. So you can calculate that in. I prefer 2-bit radians, but you can also put it in degrees. I think in the notes they put it in the degrees, but then radians works better because most of the time we use that. Then our z value is the same as z, so z equals z, which is 3, I believe. Yeah. So that's our cylindric coordinates, as you can see. Then for our spherical coordinates, for this should be, let's say, so then our let's say spherical coordinates for p will be something like this. P, then here we calculate r of the system, and then you know r is what is squared y squared plus z squared, right? Which will give us somewhere around, I think it's 7, or you can go through that. Then our theta, you know, it's what, 10 minus 10 in this case, yeah, due to what do you call, in this case our fee, I mean, not our fee. Then our fee will be y over x, which was same as what, 4 3, right? Then there is our theta, which will be 10 minus 1. Then we get our value, square root x squared plus y squared divided by z. So it's in terms of z, which will give us um, more or less it's 64.62 degrees. So that's more or less for, and then therefore our values for, then our spherical coordinates of p will be, mm, a spherical coordinate for p will be 7. Then our theta here, which was 64.62. Then we'll have our angle, our phi here. So that's our spherical coordinates for p. Then let's see our spherical coordinates for a. And just remember, in this case now a is a vector more or less. So we have to do vector multiplication for a. So like this. So we are given our a was, so our spherical and cylindrical coordinates for a was something like this, ay, and we'll make our az to be 0, az, and that works better. And now remember, this one is given in terms, in a form of a vector, right? So we'll be using this formula here to find our cylindric values, which is cos theta sin theta 0 sin theta cos theta 0 0. And I hope you did understand how they derive this the following formula. Then our ax will replace with the our a, what do you call our a. So in this case our ax will be y, then a then ay will equal x plus z, then our az will equal 0. So this will be y x plus z and 0. Now it's just simple matrix multiplication, which I think which I believe you should know. So this is just simple matrix multiplication. So if you just do that, then you should get the following or something like this. Then this will be, then our AP will be, if you do the matrix multiplication, then it is y cos phi plus x plus z sine phi, right? Then our A phi will be minus y sine phi plus, which is what, cos A plus z cos phi. And for our Az is there is nothing, which is 0. So then our coordinates for A will be in spherical or in cylindrical coordinates. I won't write the whole thing, but it will be AP and AFE only because our AZ is 0. So, or you can put it there, it's not a problem. So that's our coordinates for, what do you call it? That's the cylindric coordinates, I believe. Yeah, it's the cylindric coordinates for A. Then you can do the spherical coordinates. I think so. I leave the spherical coordinates for you to do that. That's for you to do. Yeah. Then if you want to find other values for A and Y, you can do that. But then they say I wanna address another thing here. Then for you, you will do the spherical coordinates is the same way. Then they say evaluate. Then this question here. They say now you need to evaluate what you call A at point P in Cartesian, cylindric, and spherical. So what do they mean by that is, A at point P is just, you need to remember that the value for A is where point P is in a space. Let's say we have a coordinates here. That's our point P, right? So they say A is also there, right? So if A is there, so therefore the value for x of P is same as the value of x of A, right? Or maybe let me redraw this side. So they mean evaluate A at point P. So let's say we have this diagram here. I'm just doing that in two-dimensional, and somewhere here is P. Or let's just say P is somewhere here in space. So that is our P. Then they say evaluate A at P. So that's, well, simple English just means point A is where P is, so that is the same point. So therefore, we know what do you call A must be the same as P. But in this case, our A is also equal to what? Y of x plus z plus A of y, right? So therefore, you can say the values for this, it's going to be more or less the value, the x value of, I'll see P will equal x of value of A, y value of P will equal y value of A, and z value of P will equal um, z value of A. So therefore, you can substitute those values in your web. Py is what, 6, so let me just write it there. That will be minus 2, 6 and 3. So we can say our 6 of A of x, then x is um, minus 2 plus 3 A of y. Then it's going to 6ax plus 1ay. So now they say you get this value here now. Now you use this in the formulas to calculate the, what do you call, to calculate the spherical, cylindric, and Cartesian coordinates. So it should be more or less similar to that. So you'll calculate the spherical, Cartesian, and all those coordinates in the for that. So you can say the Cartesian is already given. So you'll be calculating the what do you call, spherical, and yeah, and what do you call, the cylindric coordinates, that will give you all the values. So you'll use this formula again here, the, or you can say the formulas you'll use. The formulas you'll use is all these formulas. You, you have the values now, so you'll use these ones to calculate your, what do you call, that this one is for your cylindric. Then you'll use this formula. It's theta, that's phi, to calculate your spherical, where you saw your, what do you call, A is now. It's 6x and plus a y, and then your az is 0. So we'll make that 0. So yeah, that's simple enough, I think. And that's it. For the examples that are given here, and then there are some exercises you can go through, such as exercise 6, where they say uh, P is perpendicular to a module Q, and or okay, P and Q are there, and if R is 8 and R is perpendicular to the both, so you are just finding the unit vector of this system. So, and I think so you do know how to find the unit vector, which is given here. As they say, our R is perpendicular to the both of them, and that's the gradient of R, or the magnitude of R, I mean, magnitude of R. So your AR is given, then you use this formula to calculate the unit vector of R. Then you multiply that by 8, or yeah, it's 8, and that gives you the value where R is in the space. Or so perpendicular just means you're finding a unit vector to a point. Then this is a class work. I think so. It's simple enough. You can go through it. Exercise 7, it's simple enough. Where they say given point is P, where R is 150. So this one is your, I think so it's given in. If you can see it's spherical coordinates, then you must find the Cartesian and cylindric, which is simple enough, which you can go through it yourself. Then there's a solution for that. For 7.2, then there's a class work where they say you are given this system uh, to convert it into a, which is again it's just a repetitive repeating the process just makes it easier for you to understand or know what needs to be done. So yeah, you can go through this and the answer is given here. There are exercises which are in the textbook and I think so I did give you the I think so I do should have all the notes in the textbook so that this shouldn't be a problem. You can go through it. Yeah, then that's homework you can read through it and we are done. And we have our assignment here, assignment one, which I think I'll give you until next week Wednesday to complete it, but I'll announce it. Yeah, so more or less we are done with chapter one. Thank you.